Hello everyone, I'm Joseph Kuruvilla, a postdoctoral researcher at Université Paris-Saclay. Today I'll be talking to you about 3-point Gaussian streaming model for Redshift-Space Distortion. This talk will be based on a recent work with Cristiano Pocciani. I will start the talk with a brief introduction to Redshift-Space Distortion. In astronomy, the third dimension is given by the redshift to an object. However, the observed redshift is affected by both the cosmological expansion and the peculiar velocity along the line of sight. Hence, the three-dimensional maps of the universe we obtain are distorted. To pictorially explain, we here show a slice from the n-body simulation we employed in this work. On the left panel is information from real space or the unobserved reference frame. And here clearly we can see some cosmic web elements. High dense regions called as the clusters are denoted by orange points here, while there are also features like the filaments running along this slice. The underdense regions are denoted in black in color, called the voids. So here and for the rest of the work, we are under the approximation of a distant observer or plane parallel approximation, where we approximate the line of sight to be along a fixed axis. In this work, along the z axis. And now we recreate the redshift space or what we observe in real life. So what can see is that clearly there are different patterns when compared to the real space and the redshift space, and there are also the collapse structures on the nonlinear structures appear elongated along the line of sight. This effect, this nonlinear effect, is called the finger of God effect. And Redshift-Space Distortions has matured to be a tool to test theories of gravity. On the right figure taken from Ala et al. 2017, what one can see is that using Redshift-Space Distortion and one can constrain the growth rate times the sigma 8 parameter as a function of redshift. Here different points correspond to different surveys. And with the solid line with the blue band corresponds to the Planck lambda CDM prediction, assuming that general relativity is the correct theory of gravity. With the forthcoming redshift surveys, the measurement of the constraining power of growth rate will get better, and we will have smaller error bars, and thus the redshift space distortions will be an important tool to test theories of gravity. Thus, there is a growing interest in extending RSD studies to smaller and nonlinear scales, but also to extend to higher order clustering statistics in addition to what's been done already for the 2-point clustering statistics. As I mentioned, most of the constraining power for so far has been for growth rate has been done using in configuration space has been done using the 2-point correlation function. So here again I show on the left panel the real space, and on the right panel the redshift space correlation function. On the left the x-axis is the perpendicular separation between pairs, while on the y-axis is the parallel separation between a pair. So what one can see is that while measuring from the simulation here, on the real space we see the isotropy of the correlation function as expected, while on the redshift space there is an isotropy in the correlation function. By leveraging the degree of an isotropy, one can measure the growth rate of the structures. And thus the main goal in RSD modeling is how to map from the left, which is the isotropic, to the right in the anisotropic redshift space correlation function. In configuration space, one of the main frameworks has been what is known as the streaming model. So the streaming model gives us the anisotropic correlation function as an integral from the isotropic correlation function times a relative pairwise velocity distribution. This was put forth by Peebles in 1980s, subsequently worked by Fisher and Scocimaro among others. So in configuration space analysis, for this is the current workhorse is the Gaussian streaming model, where the P2 or the relative pairwise velocity distribution is approximated with a one-dimensional Gaussian. And this Gaussian streaming model has been used in Bose analysis to constrain the growth rate. and also in the recent EBOS analysis as mentioned given in these papers. And this have led to precise measurement of growth rate of structures. So now the question is, it has already been shown in Fourier space that by combining power spectrum and bispectrum, one is able to gain in cosmological information gain. And so the question here was, can we generalize this the streaming model to 3-point and higher order statistics? And what we realized is that we can indeed generalize it. Starting from first principle, we generalize the streaming model framework to n-point statistics. Analogous to the 2-point information, what we saw is that the anisotropic n-point full correlation function in Redshift space can be obtained as an integral of the isotropic n-point full correlation function in real space times the joint probability density of n-1 relative line of sight peculiar velocity. It should be noted that this equation is exact under the distant observer approximation. So now to diagrammatically show what the full correlation function in 3-point is, it would be 2-point correlation function plus the connected 3-point correlation function plus 1. And thus the 3-point streaming model can be written as given in the latter part of this slide. So it would be the full correlation function in 3-point in Redshift space would be 1 plus psi s plus 3 times psi s plus zeta, where zeta is the connected correlation the connected 3-point correlation function. And it can be now the main ingredient is that the velocity information p3, which depends is a function of the 5 triangular sides. Now the question is, what does this p3 look like, or the joint probability distribution of 2 relative velocities look like? So using n-body simulations, we directly measure this PDF. On the x and y axis are the 2 relative pairwise velocities, while on the x axis we show the amplitude of the PDF. And one can see that the PDF is clearly unimodal, and at this on this triangular configuration, naively one can take an initial guess for this to be a bivariate Gaussian. And we also show the marginalized the pairwise distribution for this triplet in the black line. Now the question is, can we predict the velocity moments from theory itself? And what we here show is the first moment, the mean of this bivariate distribution. We fix a triangular configuration, the 4 sides of the triangular configuration as denoted in the top of this figure. And on the x-axis, we let the 5th side, which is the R31 perpendicular in this case, to vary. And on the y-axis, we show you the mean velocity of this bivariate distribution of pairwise velocities in a triplet. The symbols here denote the direct measurement from the n-body simulation, while the solid line and the dashed line denote the analytical prediction from leading order in perturbation theory. The analytical prediction was obtained using the equations as shown in below, where the W bar here is the pairwise velocity in 2-point, and mu here denotes the line of sight angle between the angle between the line of sight, and the mu12 here means the line of sight angle, the angle between the line of sight and one side 1,2. And subsequently we can look at the second moment of this distribution. So again it follows the same convention that the symbols denote the direct measurements from the n-body simulations, while the solid line and the dashed line are the analytical predictions from theory. Here the fidelity is quite high, but only about 40 to 50 megaparsec. Unlike in the case of 2 points, in the case of 3-point, we also have a cross moment for the second cross moment, and this also can be analytically predicted using perturbation theory. So here we show the prediction using in the solid line and we all and the analytical prediction can be shown can be obtained from the equation above, where psi parallel is the velocity correlation along in the line of sight velocity correlation, and sigma v square is the one-dimensional velocity dispersion here. So combining this information, we can see that while the mean velocities are able to be predicted using theory quite to high fidelity, even to smaller scale, the same cannot be said for the dispersion, the second moment here, which starts to fail above 40 megaparsec. However, using the simplest implementation of leading order in perturbation theory, we are able to achieve high fidelity above 40 megaparsec or so. So now, putting together the ansatz of using a bivariate Gaussian and using the velocity moments from perturbation theory, we check how good is the resulting approximating PDF when compared to the direct measure from n-body simulation. To quote John von Neumann, truth is much too complicated to allow anything but approximations. And here the direct measurements from the n-body simulations are given by the dashed contour lines, while the prediction using the bivariate Gaussian ansatz plus the velocity moments from perturbation theory is given by the solid line. And we try to statistically quantify what's the information loss connected to this approximation. So for this particular triangular configuration, and similarly for the rest of the configurations along these scales, we found that the Gaussian approximation is nearly lossless. We measured the Jensen-Shannon divergence statistics, and we found out that it was the information comes out to be about 0.005 natural units. So just to give you an idea, the Jensen-Shannon divergence is bound between 0 and 0.693, implying that the information loss by using a Gaussian approximation is quite low. So now we introduce the 3-point Gaussian streaming model, which is the phenomenological model we introduce. So the simplest implementation consists of velocity moments from standard perturbation theory at leading order, and using a bivariate Gaussian as the approximating PDF for P3, and we evaluate real space 2-point correlation function and 3-point correlation function at leading order in perturbation theory. Putting this together, we get the anisotropic correlation function in Redshift space. On the left panel is the full 3-point correlation function, while on the right panel is the connected 3-point correlation function. So we measure the full 3-point correlation function using the natural estimator, that is DDD over RRR, where D denotes the data while R denotes the random points. And for the connected, we use the Sapodi-Saleh estimator. We also have predictions of the 3-point Gaussian streaming model for 3 cases. The 3 cases vary from each other depending on how we change the input of 2-point correlation function and 3-point correlation function. In case A, we use the leading order in perturbation theory for the 2-point correlation function psi. However, we set the connected 3-point correlation function to be 0, and that's denoted by case A, while case B uses both psi and theta using leading order in perturbation theory. And in case C, we wanted to understand how the nonlinear evolution of 2-point correlation would affect this prediction. We used the psi from the 2-point correlation from Halo model, while still using theta from leading order in perturbation theory. And for the full 3-point correlation function, we find all 3 prescriptions are quite similar to each other. However, when we come to the connected 3-point correlation function on the right panel, we see that case B and case C are favored over case A. However, here the signal to noise ratio of the measurements itself is low, so that seems to be a disadvantage in this case. However, this comes from the fact that in the anisotropic correlation function is a function of 5 triangular separations. Here we fixed 4 separations as denoted in the top of the panel, and we let the side S31 perpendicular vary. So looking here, we see that at least case B and case C produces the measurement quite well. However, since the signal to noise ratio were quite low for the anisotropic case, we tried to see how we can do a compression of this information and obtain a higher signal to noise ratio. So for this purpose, we checked how connected 3-point correlation function and the 3-point Gaussian streaming model prediction works for when it's spherically averaged. On the left panel, we show the real space correlation function, and on the right panel we show the Redshift-Space correlation function. We show the real space as a test for our input ingredient. The test for 3-point Gaussian streaming model is only good if the input ingredients itself are of high fidelity. What we see here is that on this triangular configuration, the theory predictions, the perturbation theory predictions for real space 3-point connected correlation function is not the best, and it can be improved. And then we check, however, we still use this as the input for the 3-point Gaussian streaming model, and we still check, and on the right panel we see the spherically averaged quantity here. So where the blue solid line gives the 3-point Gaussian streaming model for case B, where case B again is that theta, the input real space correlation function for 2-point and 3-point comes from the leading order in perturbation theory, while case A is basically using 2-point correlation function in leading order in perturbation theory and setting theta, or the connected 3-point correlation function, to be 0. So what we can gather from here is that the 3-point Gaussian streaming model in the case B recovers the n-body signal, or the measured signal from the simulation, quite well. It should be noted that there is no fitting anything of sort here. Rather, we just use the theory prescriptions and using 3-point Gaussian streaming model to compute the correlation function. It's also interesting to note that in case A, there is still a non-zero contribution to the Redshift space 3-point correlation function, even though our input theta is equal to 0. This tells us that there is a contribution of Redshift space correlation, the 3-point correlation function, from purely 2-point correlation function and the velocity information. So we also considered another compression statistics here, basically the wedge statistics in 3-point clustering. So here the columns denote the binning from mu1 2, and the rows denote 2 different binnings for mu2 3. This is a very small subset of what we show in the paper. On the y-axis we show the clustering information, the amplitude, and what we can see is that the solid lines reproduce the symbols quite, or the n-body measurements, quite well. Now, so far we started by saying Redshift-Space Distortion is a good tool to measure growth rate. However, we wanted to see how Redshift-Space correlation function depends on the growth rate of the structure. So what we found out is that the 3-point correlation function is able to assist in breaking the F sigma 8 degeneracy when combining. So on the left panel here we show the G3, or the full correlation function, which is dominated by the 2-point contribution, while on the right side we show the connected correlation function, and we see the dependence on the F sigma 8 plane is different, and this suggests that if we were to measure the Redshift space correlation function with sufficient accuracy, it can help in breaking F sigma 8 degeneracy. The similar conclusion was reached based on Fourier space statistics as shown in Gilmarin et al. 14. We also fixed the sigma 8 and changed the growth rate to see how the 3-point correlation function varies, and what we were able to find out is that there is indeed a variation in the 3-point correlation function and is sensitive to the growth rate of the structure. Now, to conclude, as the statistician George Bock said, all models are wrong, but some are useful. As a takeaway point, we say that For the 3-point, we have introduced velocity moment predictions using perturbation theory at leading order and compared to simulations and produce high fidelity. We also introduced a phenomenological model for 3-point correlation function, which we call as the 3-point Gaussian streaming model. Our results suggest that the 3-point correlation function in redshift space can help in breaking F sigma 8 degeneracy. So as a short outlook would be to apply this model to bias tracers and also use more sophisticated perturbation theory flavors like CLPT or CLEF or the convolutional Lagrangian perturbation theory or convolutional Lagrangian effective field theory. Thank you so much for listening. Thank you.